All right, guys, so we're going to be looking at solving equations with logarithms, and two types of equations with logarithms: equations that already have a logarithm in them, and also equations that you need to use a logarithm to solve that might not start with one. So lots of solving. We're going to do basically 2 days on this, a full, a whole bunch of examples that we'll look at today. And then next class, our quiz will be at the end of class, and we will do like some review of solving all types of equations. So both like same base and not the same base, and all the different stuff we look at today. So yeah, there's a lot of different types of logarithm equations here. So I'm going to try and give you guys some strategies, and we'll look at a lot of different examples so you can see. Mike, will you close that computer, please? So here are some general strategies or methods here. So we have this thing called exponentiate. Exponentiate is a verb, or exponentiating is what we're doing. This means two things. This means either rewrite in exponential form, but another way to think of that is it's actually turning both sides into exponents. So it means both of those things. And again, you might remember this from last year, but if not, it's okay. This will make more sense once we do some examples. Usually a good strategy is condensing logarithms. I almost wrote condense them completely, but actually sometimes, usually we want to condense them all the way. Let me just say usually. Sometimes we'll expand them slightly, and there's lots of different methods here. This is just a strategy. Let's see. Be prepared to factor. And then usually it's helpful to get the logs to one side of the equation. But again, these are more like strategies, things to try. Not necessarily 100% of the time do we want to get the logs to one side, just usually. So I've got a variety of examples that we're going to do together, and you'll kind of see some common themes, and then you'll practice them on your own, and all that good stuff. So lots of different twists and turns here. We're going to start with some basic ones. But they don't necessarily look basic because there's letters, a lot of letters in there. So with this one here, if we have a situation where we have a log and then a variable equals a number, this is a situation where we want to exponentiate. And again, there's two ways that you can think about exponentiating. One is just rewriting this as an exponent. So if I rewrite that as an exponent, what is the base of natural log? E. And then what is the exponent? Which part of this is the exponent, the x or the 6? The 6. So e to the 6 equals x. And that's actually our answer, e to the 6. E to the 6th is just a number. Let me pull up my calculator here. You won't have a calculator for this, so e to the 6 is like fully simplified. But just so you know, e to the 6th power is 403. So e, remember, is this number that equals 2.71, etc., etc. So well, you'll just see that in your answers every now and then. So e to the 6th simplified all the way. But let me just show you what it means to make both sides exponents in this equation, because that's also what exponentiate means. What we do is we have the same thought process. What's the base of natural log? Oh, it's e. So we make both sides of the equation powers of e. So it's e to the natural log of x equals e to the 6th. And the idea is that when we do that on this side, the e and the natural log, they are inverse operations, so they undo each other. So we are left with x on that side equals, and then we just have e to the 6th on this side. And so it's really two different ways of thinking of the same process. We're getting to the same answer. This way is generally better to think about doing that, making both sides exponents. Sometimes, yeah, like rewriting as an exponent is good, but really we want to just make them both powers of whatever base we're talking about. So that's kind of how I'll refer to it from now on. Hello. So let me just write that in here. Make both sides powers of e. This way is better. Okay. Kind of similar process here, just in reverse. We can either rewrite this as a logarithm. Turn to your neighbor. What would this look like rewritten as a logarithm? Okay, so I'm hearing you guys say that natural log of 4 equals x. We're just rewriting it. That's log base e. The answer over here is what goes inside the log. Remember, this number here represents the exponent that turns e into 4. And that's what we can see happening right there. X is the exponent that turns e into 4. But again, it's actually going to be better to think about taking the natural log of both sides. This is going to be a more, like, I don't know, a more better way of thinking it. Let's just put it that way. Thinking of it, taking the natural log of both sides. So when we have e to the x or e to the something equals 4, or e to the something equals something, we want to use the logarithm that has a base of e. Oh my gosh, I can't write this morning. Hello. Ln. So we make both sides inside the logarithm. We take the log, the natural log of both sides. Same thing here. These operations undo each other, so we get x equals natural log of 4. This is how we want to think about it, instead of rewriting it. Because the more complicated these get, the more difficult it is to think about what rewriting it actually looks like. Okay. All right, so give this one a try. Okay, so turn to your neighbor. What would be your first step here? Okay, so our first step, again, we could either think of it as rewriting it as a logarithm or taking the natural log of both sides. We have e raised to a power. Natural log is the opposite of that, so we write this as natural log of e to the 4 minus 3x equals natural log of 6. The natural log and the e, they undo each other. So 4 minus 3x equals natural log of 6. And so what we're going to do now is just solve for x. So natural log of 6 is just a number. It's a strange decimal, but we need to get x by itself. So we're going to subtract 4 from both sides. And I'll usually write it like that just so that you can tell that there's nothing inside the parentheses with the 6. And then we just divide by negative 3. And so that's our answer right there. Or you could write it as, natural log of 6 minus 4. Just make sure that you don't get confused and think that it's 6 minus 4 inside the log and make it natural log of 2. Don't do that. All right, give this one a try.
I just did 2 of
Okay, so here's how we want to think about this one. We're going to exponentiate, which means we're going to make both sides exponents of 2. You could also think of it as rewriting. This will be the last time I say that you could think of it 2 different ways. I'm now just going to refer to this. So 2 to the log 2 of 7x minus 6 equals 2 to the 3rd power. On the left side, the 2 and the log 2 undo each other. So we have 7x minus 6 equals, and what's 2 cubed? 8. So then we just solve from here. Okay. Here's our next one. Turn to your neighbor and talk about this one. What do we think we could do here? What are some of our strategies or methods? What might work with this one? So what do we want to do with the log on the left? What can we do with that too? So we have log 6 of x squared equals log 6 of 16. Now, yeah, we might be able to see x equals 4 right here. If we have log 6 of something equals log 6 of something, it must be true that those two things equal each other. So we're setting the insides equal. Now, one of the strategies I said earlier was that it's good to get logs to the same side of the equation. I'm not going to do that here because there's just two logs and they have the same base, so there's not a need to do that. We can just set the inside equal. Does anyone know the fancy math word for the inside of like a logarithm or some other function? Like x squared is an example of this, 16 is an example of this. Anyone know? No, it's a general thing that refers to like the inside of something. So like natural log of blah 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 blah, whatever this is, no matter what it is. It's a phrase that refers to the inside of a function. It's called the argument. So it doesn't get used that often in math, but that's what it means. Like the inside of the natural log is called the argument. So what we're doing is we're setting the arguments equal. Okay, so if we get x squared equals 16, actually that would tell me that x equals 4 or x equals negative 4. So always remember you want to think of a positive and negative solution, except we cannot take the log of a negative number. This is an extraneous solution. So I could say the argument of a log must be positive. Remember our graph for logarithms? Our parent graph looks like that. So this could be a graph of like log base 2 to the x or whatever, log base b to the x, let's just say. And remember our domain goes from 0 to infinity. So the x can't equal 0 or any negative number. Or another thing to keep in mind, like if I have log 2 of negative 2, is there any exponent that can turn 2 into negative 2? Can we raise 2 to a power and get a negative number? No, we can't. We'll always get a positive number. So the inside can never be negative. So we will need to test for extraneous solutions. Okay. Like I said, I've got a variety of problems here for you guys. Okay, turn to your neighbor and talk about this one. What strategies might we use? What could be our problem-solving process here? Okay, what can we do as our first step here? Any thoughts? Yes, we can condense. So this becomes log 6 of x plus 3, and then what? If I'm just condensing right now. What's the next thing? X plus 3? times x plus 4. Exactly. So you can write it like that, or if you want to put like some brackets around there or a big set of parentheses just so that you know it's all in the log together, equals 1. So I always like to condense logs when there are logs and constants. So we have 2 logs and the number 1. Whereas in the last question, we just had 2 logs. So that's a little more specific of a strategy. Then our next step would be to what? Yes. So I'm going to exponentiate here. I'm going to make these both powers of 6. So I'm left with x plus 3, x plus 4 equals, what's on the other side? 6. What should I do with this? Yeah. And so remember, just a quick way to multiply that, the middle term is going to be these 2 numbers added, right? And the last term is going to be them multiplied. Next step. What do we do next?
The 6 to the other side of 5.
Yes, sir. So remember, one of our strategies is be prepared to factor. How does this factor?
X plus 6, X plus 1.
Nice. So x equals -6 and -1. Okay. Maybe both of these are extraneous solutions. Maybe just one of them is. Which one, if we plugged it into the original, would make the inside of the log, the argument of a log, negative? -6, right? -1 is actually okay. It would make this 2, and it would make that 3. So that's okay. But -6 is not going to work. Okay, questions on that one?
Why does -1 work?
-1 works because when I look here, x plus 3, if it's -1 plus 3, that's still positive. And same thing over here. That's still positive. Okay. Let's see. We got log 96x minus 12 equals 2 plus 1x minus 2. We've got 2 logs and numbers.
But I guess I can just want to try that. So, now I think we can just do
Usually it's have like 4.
Okay, let's talk about this. There's actually like 4 ways that we could solve this. The way that my default way of thinking about it is I see 2 logs and a number, so I want to get the logs together. I want to combine them. And so I subtracted log x minus 2 from both sides. But I'll show the other ways to do this as well, because just because if you didn't do it my way, you could still get the right answer. When I see logs subtracted, I combine them into what? Subtraction between logs becomes division. So this is 96x minus 12 over x minus 2 equals 2. And now I can raise them both as exponents of what base? 10. This is log base 10. So again, if you did it a different way, you might still, the way you did it might be fine. So I'll show multiple ways. So what we get on this side is 96x minus 12 over x minus 2 equals 100. And as I'm solving for x here, I just multiply both sides by x minus 2. So we get 96x minus 12 equals 100, x minus 200. And so I get 4x equals 188. And I think that's something like 43. So my strategy is usually combine the logs together, then I can exponentiate both sides, and I just have 1 log equals 1 number. Just copy this. But there's other ways that we can do this. Will, what was your first step there?
Set them all, like, make them all.
Yeah. So if we raise both sides as powers of 10, the only key with this is that we have to raise the entire side. So this is 10 to the 2 plus log x minus 2 equals 96x minus 12. So the whole thing becomes an exponent of 10. I can't do it separately to the 2 things. This side here, the right side, my exponent properties say that when I have 2 exponents added, it's the same thing as multiplying the bases. So this is 10 squared times 10 to the log x minus 2, like that, which then becomes 100 times x minus 2 when those cancel out. So you see we're at the same place. We get the same answer. So again, that's why I'm showing you guys some different strategies and methods, because a lot of these can be thought of in different ways. Okay. Let's keep going here because we got a few more. We have 13 total. So let's just so you know, just so you can have good expectations. Some of them are shorter than others. Talk about this with your neighbor. What do you do?
Yeah, do like exponent.
Okay. There's 2 ways to do this one. If I just raise both sides as powers of 2, I get x cubed equals 2 to the 12th. We don't have calculators, so 2 to the 12th is pretty big. I don't know what it is off the top of my head. But if I'm solving for x, what operation would I do to get x by itself? Cube root, yeah. We would cube root both sides, or what's cube root as an exponent? Not divided by 3, but it's x to the 1/3. Yes, we can raise both sides to a 1/3 power. And so this becomes x equals 2 to the 4th, yeah. Which is 16. I do know that one off the top of my head. Or, what could we do with this exponent right there? Where else could we put it? Yeah, on the front. We can make this 3 log base 2 of x equals 12. And then we could divide both sides, by 3 and get log base 2 of x equals 4. And now when we exponentiate, we've already divided by 3. I mean, this is really a, tomato situation, whatever makes more sense to you. In both cases, you have to divide 12 by 3, and it's 2. The answer is 2 to the 4. So, some different methods. Okay. The next two are very similar. Oops. Both of these have the same method of solving. And both of them look really complicated. Turn to your neighbor. What the heck could we do that's the same that would solve both of these? What could our method be? Okay, the method for both of these, Peyton? What's that word that you said that starts with F? You can factor it, yes. So what we want to see here, very nice, is I'm just going to substitute the letter u in for a natural log of x. Because what I see here is u squared minus 4u minus 12 equals 0. I didn't use x just because x is already in the question. But this is this is just back in the day, classic factoring. This becomes u minus 6, u plus 2 equals 0. So u equals negative 6, u equals 6. And u equals negative 2. And on the other one here, if u equals e to the x, e to the 2x is the same thing as e to the x squared. Because we'd be multiplying those. So if we rewrote this, this would be u squared plus 6u minus 16 equals 0. How would that one factor? U plus something, u minus something.
10 and 6.
10 and 6. 10 times 6 is 60. 8 and negative 2, yeah. So then u equals negative 8 and u equals 2. Okay, now, our goal in this is to solve for x. We've solved for u, but we haven't solved for x. So far the problem is the same for both. Slightly different here. Our next step would just be to substitute back in. Natural log of x equals 6. Natural log of x equals negative 2. So how would we solve both of those?
We'd have to do, like, since, oh wait, I guess we'd have to do, like, e to the 6 equals x.
Yep. And this would be x equals e to the negative 2. Or we could say x equals 1 over e squared. Either one is fine. So we have to exponentiate to solve that one. The other one, we're left with u in this case is e to the x, so e to the x equals negative 8. Or e to the x equals 2. How do we feel about those? Is it possible for e to be raised to a power and become negative? No, e is like 2.7, so that one's impossible. This one we solve by taking the natural log of both sides. So natural log, so we get x equals natural log of 2. So that's what I mean about be prepared to factor. We want to recognize that these can be treated as though we're just solving for a quadratic. Okay, save the best till last. Okay, so what we need to recognize here is we cannot get these to equal the same base. They're not both powers of 2 or 3 or anything like that. And so we have some options here. We could take log base 6 of both sides, which would cancel out the 6 but not the 5. We can take the log base 5 of both sides, which would cancel out the 5 but not the 6. Or we can take the natural log of both sides, which wouldn't cancel out either one. And actually that's what we're going to do, because in the long run we end up using natural log way more, especially in calculus. But either one works, and if you can figure out how to do it with log base 6 or log base 5, that will work. But here's what we do. We take the natural log of both sides. We move the exponents down. And make sure you keep them in parentheses. We distribute. So this is going to start looking really complicated, but sometimes math looks complicated. We're going to get the terms with x in them to one side. Doesn't matter which side. I'll just move x to the left. So I'm going to subtract 2x natural log of 5 from both sides, and I'm going to move the other terms to the other side. Once we have the x's on one side, we can factor out x. And we just have one more step and then we're done. How do we solve for x? Well, yes. Just divide. Okay, so that process is always the same for those types of questions.